Hi everybody. We're going to continue with chapter 13, which is reactions of alkynes, and then I think we might be jumping into 15. So we skipped 14 in the way I teach this class. Alright, so yeah, where were we? Where were we previously and where are we going now? Well, we started talking about the different kinds of reactions of alkynes, and this is one of the ones we showed last time. Markovnikov reactions of alkynes. This example is a little weird, being, you know, Markovnikov, which means addition to the substituted side. In the example we're providing here, it's like, well, there's not really a more substituted side, but really, you know, after one bromide adds, I guess it's Markovnikov because of how the second bromide adds and is incorporated, and it winds up at the same place as the other one. That's, I guess, why we call it Markovnikov. Yeah, this is all from last time. I think maybe one cool thing that was new here was this concept of an RSCC, which is a resonance stabilized carbocation. It's this weird thing that carbon double bound to bromine, which is actually a resonance structure. These are resonance structures. Anyway, but since it's stabilized, it is, you know, more likely to form this way, and that's kind of why that explains why it's actually Markovnikov, is because you're forming something that's sort of stabilized. If HBr would have added in the opposite direction, right, and the carbocation would be over here and the H would be here, right, then it wouldn't be stabilized, and that's why it's Markovnikov. It's Markovnikov because it's going through a stabilized intermediate. Right, so that's one of the things we learned about. What else did we learn about last time? We showed this. We showed this oxymercuration reaction. Oxymercuration is another Markovnikov one, and that gave you ketones. So, like an alkyne would be converted to a ketone. One difference between oxymercuration of an alkyne versus an alkene is that for alkynes you use mercury sulfate, HgSO4. For alkenes, remember alkenes from Organic 1? It was Hg acetate, HgOAC2, right? So it's a slightly different mercury reagent. But this is totally, we went through the mechanism, and, you know, which explained why it's Markovnikov. In a nutshell, it's because this thing you make, when the alkyne attacks mercury, it makes a mercuronium, and as we talked about, this kind of acts like a secondary carbocation, which basically means that nucleophiles are going to attack this middle secondary position like water, and that's how oxygen gets there. And then just a couple more steps, and then you got a ketone, and including this tautomerism thing that we talked about. So this is all last time. You can review it from the last lecture. What else did we do? Oh yeah, so I guess this is kind of where we left off, and where we're going to continue is anti-Markovnikov addition to alkynes. And like the idea is, if you, rather than using HBr, using HBr peroxides, you can get bromination exclusively on the terminal position, okay? And that is due to this radical mechanism, and we'll talk about the radical mechanism in a second. This is the same exact radical mechanism that you saw for alkenes, and we're just going to do it as a single HBr, so it puts a single Br on the terminal position. And remember, it also makes a mixture of cis and trans. Okay, so let's do the mechanism now. Alright, so let's show this mechanism now of how we can do an anti-Markovnikov addition to alkynes with a radical addition of HBr, and we're going to do one equivalent specifically, so just one equivalent of HBr. Alright, so alkyne, make sure you draw the alkyne correctly. Remember, don't draw like a bent alkyne or something like that. It's a linear arrangement. We also have an H that kind of extends out. We're going to skip that H, okay? So we don't need to draw it. HBr peroxides. By peroxides I mean typically tert-butyl, ditert-butyl peroxide. So it's tert-butyl, tert-butyl. These are tert-butyl groups, right? 4 carbons each, tert-butyl. And we have a couple oxygens in there. Okay, and yeah. So 1, 2, 3, 4, 5. 1, 2, 3. Oh, see, I messed up. Extra carbon. 1, 2, 3, 4, 5. And then the Br. This is trans, of course. Now we also have cis, but that's kind of not really the point here to worry about stereochemistry, because stereochemistry is not a big deal. It's not really controlled. It's a mixture of cis and trans. Okay, so how does this work? Mechanistically. Alright, so the first thing is that kind of like a little mini step happens where we have tert-butyl, tert-butyl, and this makes a pair of tert-butoxy radicals. So I'm drawing like a mini step in brackets here. And this is radical chemistry, right? We said it's a radical addition. So what's the mechanism? And what kind of arrows do you use if it's a radical mechanism as opposed to a non-radical mechanism? Remember this? Organic 1. Maybe chapter 3 where you learned about radical halogenation, radical bromination. So we don't use normal arrows, like the normal arrows, the reaction mechanism arrows. We use fishhook arrows, right? And that shows single electron movement. So this is basically, we might assume a little bit of heat also. This is a weak bond, and the bond just ruptures. And so one electron goes one way, one electron goes the other way, we get a pair of radicals. Okay. Alright, so now one of these reacts with HBr. One of these reacts with HBr. So oxygen loves hydrogen. So if oxygen can get a hydrogen, it's like kind of happy, especially an oxygen radical, which is not a stable radical. So this radical will just rip off a hydrogen from HBr and make a Br dot. So now it's 3 fishhooks. Fishhook, fishhook, fishhook. Fishhook, fishhook, fishhook. I could make this a little better if I draw HBr a little larger. Like, make that bond really long. HBr. Okay. Fishhook, fishhook, fishhook. 3 fishhooks. Okay? And what does that give us? It gives us tert-butyl alcohol, which is actually a stable functional group. And what is this? Br dot. Okay? Br dot. Alright, so then what happens? Now I'm going to kind of go this way to the right. So now we're going to use that starting material. Actually, let's draw this way. Okay, so we're going to take the starting material, the initial alkyne that we have, and we're going to have our Br dot. Alright, so we have our alkyne and we have the Br dot. Alright, and so we introduced this in the alkene chapter. The idea of, one of the reactivities of radicals, like a Br radical, is that it can add to a carbon double bond or a triple bond. So in the alkene chapter they added to double bonds. In the alkyne chapter it adds to a triple bond. And when it happens, when it adds, it does so to make the most stable carbon radical possible. So I guess let me show you what happens. Alright, so fishhook, fishhook, fish hook, 3 fish hooks, right? Fish hook, fish hook, fish hook, 3 fish hooks. So the bromine is making a bond to basically to carbon. The double bonds or triple bonds breaking, and one electron's going to attach to the bromine, and another electron's going to the middle, which is on a carbon, right? And what does that look like now? What does it look like? Well, it's going to look like this, but with the bromine on it. And it's not going to be a triple bond, it's going to be a double bond. So it's 5 carbons, right? Count your carbons. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Br. Now, of course, there was an H. We still have the H, right? There was an H initially, and we still have an H. I'll draw it. You don't have to, but it doesn't hurt. Okay, there's our H. But what do we have here? This other fish hook. What did it create? A radical. Okay? And I was leading to this before, and this is, we talked about this in Organic 1 when you learned the same reaction. Why does it do this? Why does it attach to the end to make a secondary radical? Right? Why couldn't it attack this attack here and push the electron out here and it'd be kind of like a primary radical, right? If it attacks here, it's a secondary alkene radical, right? But if the bromine kind of did the, attached internally and pushed the radical to the outside, it would be more of a primary radical, okay? And the reason it does it this way is because the secondary radical is more stable. You might remember that from Organic 1. Secondary radicals are more stable than primary, right? And who's more stable than secondary radical? Like tertiary. So if the gradient in stability is, first goes tertiary, then it goes secondary, then it goes primary. And so this is secondary, this is a little more stable than primary. And that is the fundamental reason for why this is anti-Markovnikov. Why the Br goes here is because of radical stability of this intermediate. I'm going to write a couple words. I'm going to say it's secondary, right? That's good. Not really a word, but you get the idea. And I said alkene radical. This is like a secondary alkene radical. The more proper terminology, though, is called vinylic. Vinylic radical. Vinylic means on an alkene. So, and vinyl means alkene also, right? So, yeah. So this is called vinylic when the radical is actually on the alkene there. All right. So how do we finish it? How do we get to the final product then? We're very close, right? What's the difference between this and this? Well, here we have an H. Of course, here we have an H too. Right? We have H and H. Okay, so how do we finish it? Well, now all it does is it takes, we have Br and H, and it just, alkene, or the radical just takes off H from Br. And how many fish hooks is that going to be? It's going to be fish hook, fish hook, fish hook, 3 fish hooks. So, fish hook, it's kind of like a little hard to draw that. I'm a little congested here too, so okay. Fish hook. Haha, let's see if I can do this. Okay. Fish hook, and fish hook. Okay, there we go. Fish hook. So the dot grabs an H. The H gives up an electron that was in the bond, and then that creates a new Br dot. So we create a Br dot in this process, right? And then here we go. That's the full reaction mechanism, right? So this initial step is kind of an initiation process. Like this molecule breaks to make O dot, which is like in first initiation step. This takes off an H from HBr. That's kind of like a second initiation step. now you have Br dot. And now this all this stuff is propagation of like Br dot reacts with alkyne, and then alkene radical reacts with HBr. That creates a new Br dot, and then this begins a whole cyclic process. It just goes forever and ever and ever, right? Because this uses a Br dot, this creates a Br dot, this uses a Br dot, this creates a Br dot. It's a chain reaction. It's called a radical chain reaction. And then that ultimately is just converting all the alkyne to the bromoalkene with a cis isomer also. So you get some cis stereochemistry. That's the mechanism. All right? Cool. Now there is also termination. Because the initial steps are like initiation, propagation, and termination. Termination usually is like radicals reacting with other radicals. So for example, Br dot, we'll find Br dot and terminate, and that just means the Br dot is going away. We need Br dot, but what happens if Br dot goes away? So that'll kind of stop the whole reaction process, usually kind of at the end of the reaction of like, you know, so we keep generating Br dot, eventually it has to go somewhere besides this reaction, because eventually this is going to run out. We're going to run out of this when you eventually don't have any more, so then termination happens. Okay, good. Also, of course, this is the same exact mechanism and reasoning for, like, if you have alkene, remember this from chapter 12, organic 1, and you do HBr peroxides, how you get an anti-Markovnikov HBr addition here is also a, we'll say, very similar radical mechanism. That you hopefully learned in Organic 1. And yeah, you know, same thing. This stuff breaks down. You get some O dot, right? Oxygen radicals. Oxygen radicals grabs an H from HBr. That creates Br dot. What does the Br dot do? The Br dot adds to the terminal position of the alkene, and that makes a secondary alkyl radical, right? And that's why you get the Br at the end. And then that radical reacts with HBr. It's the same exact process. So now you know you can realize that this is the same in principle as this. Okay, so that was, we're on 9 still, which is the anti-Markovnikov. Let's do B, which is HBOX. Remember that, what that stands for? So that's something we use for this reaction we use for alkenes, and we use it for alkynes. And it's an abbreviation for hydroboration oxidation, HBOX. And what this does is it converts alkynes. Okay, well, remember what happened when we did the mercury thing, which was a Markovnikov reaction. Remember that? That was another reaction of alkynes. With the mercury thing, which is Markovnikov, it converted alkynes to ketones. But this hydroboration oxidation is anti-Markovnikov, and that puts the oxygen on the end, so it doesn't make a ketone, it makes an aldehyde. Aldehydes. So this is anti-Markovnikov, alright? Alright, so let's see an example, and then we'll go to the mechanism. Here's an example. So I'll have alkyne. Now, just to make your life more difficult, just like we used a different reagent for the mercury one, which was OMDM, oxymercuration, demercuration. We also have a different reagent for the hydroboration oxidation of alkynes. It's a little different than the one that we used for alkenes. So it's, but you know, it's not that different, and I'll kind of step through it. All right. So the first thing is, what's the product? If I'm going from alkyne to an aldehyde, well, I'm going to convert this 3-carbon chain alkyne to a 3-carbon chain aldehyde. There we go. See it? Carbon, 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 carbon. All right, so that's all the same. We're not adding any carbons, and it's a 2-step process. All these hydroboration reactions that we, alkenes and alkynes do it. The step 2 is H2O2 and NaOH. The step 1 will be slightly different than for alkenes. Let's just show the alkene one up top real quick, just so you remember the reagents and everything. So if I have an alkene, and I want to make an anti-Markovnikov alcohol this time, alkene to the anti-Markovnikov alcohol, it was BH3 and NaOH, H2O2. Remember that? That was an organic one. That's the anti-Markovnikov hydration, which means we're essentially adding water across a double bond, and use BH3. Okay, so the difference is this. We're not going to use BH3. We're going to use something else. It's close though. Okay, so what we use instead here is HB cyclohexane. No benzenes, those are cyclohexanes, right? So no double bonds here, it's just that. If I want to abbreviate this, I could say it's HBCY2. CY is an abbreviation for cyclohexane, right? HBCY2. Sometimes people say CY2BH. CY2BH. That's another way to draw the same idea. Okay. Alright, so the mechanism, though, is going to be mostly the same. Alright, so what I'm going to do, I'm going to flip my alkyne over when I show this mechanism. And, okay, so I just flipped it over. And I am going to, this is exactly the same as for alkenes. So if you remember the Alkene mechanism, which you probably don't, but if you do know that mechanism, it's the same thing, essentially. Okay, so just like in the Alkene mechanism, what happens is the H and the boron kind of line up with the atoms of the alkyne, and then we have like cyclohexane. Okay. Alright, so it does this, and where's my blue pen? And now I'm going to use another colored pen to show a dot, 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 dot. So it's like a four-member transition state that we're forming. So the H is going to go to one carbon, and the boron's going to go to the other carbon, right? Okay. So to do the mechanism, it's super easy. Once you get to this point, it's just like 2 electrons go one way, 2 electrons go the other way. So one atom goes to the one thing, the other atom goes, and then the alkyne kind of grabs onto the boron. Okay. And what does that give you? Well, so I'm going to draw it kind of like this, I guess. It flips over a little bit. That's fine. Whatever. B, CY2. Those are your 2 cyclohexanes. All right. So I kind of rotated it around a bit. And anyway, big thing is the boron is on one atom, the H is on the other atom. Okay. So, and why does the boron like to go in the end? I mean, you could imagine if you flip this around, like the boron could be on this side and the H could be on this side. Why is that disfavored? Is there something that maybe favors the boron being on the end and the H going on the inside? Because that's the only question is, you know, why does boron want to be at the end? Why can't boron just be kind of in the middle, right? If you can sort of envision it, I'm not going to draw it, but if the boron was on this side and the H was on this side, would these be happy? These big cyclohexanes? No, they wouldn't, because then they'd be kind of bumping into the R group, right? So these would be bumping into that. The happiest situation is for these to be out in space, far, far away from everything, and that's why boron wants to be on the end. And that is ultimately why it wants to be anti-Markovnikov, right? Because ultimately now the boron's just going to get converted to an oxygen, and then we're done. So, but that's why it's anti-Markovnikov, is because the boron wants to be on the end. Okay? Cool. All right. So, what's next? So this is where we rely a little bit on magic. There's no mechanism here. And that is conversion of the boron to oxygen. Okay, this is another thing. Again, I can go through the mechanism in office hours if you like. This involves H2O2 NaOH. I think the book might even show this mechanism, but it's not absolutely crucial. I think the most interesting thing is, you know, why is it anti-Markovnikov? And we explained why it's anti-Markovnikov, and that's because of the cyclohexanes. But anyway, this converts the boron to an oxygen. And now, do you remember this whole thing of like alkene and an alcohol and the aldehyde? Remember that? Well, this is just the same as the mercury reaction. These have names. This is called an Enol Tautomer. Tautomer, T-A-U-T-O-M-E-R. Enol Tautomer, and this is funny because this is an aldehyde functional group, right? Aldehyde functional group. But when we talk about tautomers, the options are enol and keto. So even though this is not a ketone functional group, it's actually an aldehyde functional group. The tautomer name is still called keto. So it goes from enol tautomer to keto tautomer. A little weird, huh? Even though the functional group name is called an aldehyde. Okay. And there's our product. Okay, that's it. So that's how you do the anti-Markovnikov hydration reaction. Cool. And remember this topic of the tautomerism. That's chapter 18. So I'll just write ch18. We'll talk about it. It turns out to be an incredibly easy mechanism and reaction, but it's just down the road a little bit, a different chapter. Okay. Okay, so just as an example, kind of using these reactions in synthesis, short synthesis. Let's just assume an alkene, which is weird because we're in the Alkyne chapter, but it'll be fun. This will be a fun little synthesis problem. Okay, so how could we do this short synthesis? And this uses a little bit of Organic 1 knowledge, but it's not that hard. And you need to know certain basic reactions from Organic 1, as I explained earlier. How do I kind of go from this to that? And strategically I might think, well, any squiggly lines to draw? Any squiggly lines? And it's like, yeah, I think clearly we're adding these 2 carbons, so maybe squiggly line right there. Okay, so it's kind of like a 2-carbon piece, and look at that, it has an aldehyde on it, and it's almost like we just learned how to make aldehydes from something, right? We learned to make aldehydes from what? Using what reaction? We just learned how to do it just right here, right? So if we had an aldehyde, it could be converted to an alkyne. We could convert it to an aldehyde using dicyclohexyl borane, or CY2BH, H2O2 and NaOH, right? Then we have the other issue of like, well, okay, well, let's do that. We know that, so let's do it. That's not changing. But this was maybe an alkyne. So, because if it was an alkyne, we know how to turn the terminal position of an alkyne into an aldehyde, and it's a 1,2, right? And what is step 1 and what is step 2? Step 2 is the NaOH H2O2, or H2O2 NaOH. Step 1 is the funny borane thing, the boron. It's CY2BH dicyclohexyl borane, right? Cool. Okay, and my squiggly is still there, and now it's like, well, how could I somehow install, you know where we're going, we're back, we're coming back to this beginning point with the alkene. Somehow install a 2-carbon piece, and notice the location of the squiggly line where we're connecting the alkyne potentially relative to the OH. It almost seems, we can imagine like there's 2 pieces, right? There's this piece, which could maybe be a nucleophile, like a ... negative, right? And there's also this piece. So this could be some electrophile that we're attacking. We're attacking some electrophile that would give an OH at this position. And now the question is, what electrophile? It's not, when I say what electrophile, I don't mean like this, not the alcohol, right? Because remember, there's a couple types of electrophiles that a ... negative alkyne will react with. 4 of them, right? There's a something, a something, a something, and a something. Those 4 things are like things that these could attack. And what are they? Well, they can attack alkyl halides, so like a carbon with a bromine on it, right? They can attack ketones and aldehydes. Ketones, aldehydes. What's the 4th one? The 4th one is an epoxide, and when it does attack an epoxide, then that puts the OH on the neighboring carbon. All right. So that's, we talked about this extensively already. I'm not going to review that anymore, but yeah, this would totally attack an epoxide. So the way we'd make this is just assume we have an epoxide. Okay, so if we have an epoxide, just attack with the right nucleophile and maybe some water. What's the structure of the nucleophile? Well, the structure of the nucleophile is that, right? Not exactly that, because that assumes 2 H's, but this with like a lithium or sodium on one end. So like lithium, right? We don't need the mechanism for the synthesis, but it's so easy. Why not? That's the attack, right? It's a alkynyl anion. Alkynyl anion. Nucleophilic attack opens up the epoxide. We're not done though, because it's like, how do we convert an alkene to an epoxide? This is totally from Organic 1. You need to know it. It's a 5-letter abbreviation of a chemical. Remember, 5 letters, begins with M. MCPBA. So MCPBA is the reagent that converts alkenes to epoxides. Cool synthesis problem, and that's kind of using this new reaction we just learned, the hydroboration oxidation, which is a anti-Markovnikov reaction of alkynes. Alright, so we're actually on the last topic of the Alkyne chapter, number 10. This is chemistry of Alkenyl Halides. Alkenyl means alkene, halide means halogen, like a bromide or something like that. It's funny because this is actually not really something that deals with alkynes. It's not an alkyne topic, so it's kind of out of place, but the book does this, and it's okay. Because we learned about alkenyl halides in this chapter, like how to make, how do you make this, for example. And you learned how to make that, of course. That would be a HBr peroxide from the corresponding alkyne. But anyway, so just a little bit on alkenyl halides, because there's no better place to talk about it. And first thing is there's no Sn2 reactions. You cannot do an Sn2 on an alkenyl halide. So if I have like an alkenyl halide and I react it under Sn2 conditions, like with what nucleophile would turn the bromine into a azide? Remember this, azide? N3 is azide. You might remember from your old Organic 1 days, you're like, oh yeah, well I would totally do that with NaN3. Sodium azide. Maybe a good Sn2 solvent like DMF. Okay, but this doesn't work because it says no Sn2 reactions. We're trying to do an Sn2 on an alkene and it doesn't work, and big X does not work. And the reason, of course, is to do an Sn2 you need an sp3 hybridized carbon, and this is sp2, so you can't do, the Sn2 requires sp3. This is sp2, so this is sp2, and you can't do sp3 style chemistry on an sp2 hybridized carbon, and yeah. But if this was didn't have the double bond, if it was like a single bond, well then it would be sp3. Yeah, this would totally work, right? Okay, so that's one thing. Sn2 requires sp3. Okay. However, you can use these for Grignards and stuff like that. You can use for Grignard reagents. So if I have a benzene and I have like a alkenyl bromide and I want to do some Grignard chemistry, like maybe throw in some magnesium and that makes the Grignard, and then MGBR, right? Nice happy Grignard. And then, what can I do with the Grignard? 1,000 things. But one of them would be like a tachyketone, followed by water. Well, this totally works. The alkenyl bromides are, they can't do Sn2 with them, but you can totally make Grignards on them. And so the mechanism, of course, here is that this attacks this, and you form a bond. And I'm going to abbreviate the benzene as pH. And that's the product, and of course here's a squiggly, weird squiggly. Okay, so that's like what got attached, right? So yes, you can totally do Grignard chemistry. The book mentions the Heck reaction, and it's a really cool reaction that's useful in kind of carbon-carbon bond forming reactions. I guess, you know, I'm going to show an example, but that's going to be it. And you're not going to, like, this is not on the quiz, don't worry about it. But it, you know, this kind of chemistry is very, very cool as a way to build molecules. And if you take an advanced organic chemistry class, you will see this in total detail. So let's use the same substrate, Alkenyl Halide, just that we used above. Okay. So the Heck reaction, you know, without any other detail, it's like, well, if I have an alkene, the Heck reaction kind of allows me to just take a certain platinum catalyst, PDCat, platinum catalyst, and it just magically stitches these things together. So you get alkene, alkene, doink doink, and like that's a pretty sweet reaction. And you can imagine doing some crazy like natural product synthesis or something with things like this. This was actually the guy that made this, Richard Heck. He won the Nobel Prize in 2010. Won Nobel Prize in Chemistry. In 2010. Because of the immense power of this reaction. Anyway, book talks about it a little bit more. I'm not going to talk about it anymore. And if you take an advanced organic class, either graduate level or like undergraduate level, advanced organic class, you'll learn about this and a whole bunch of things that are equally as cool, like ways to magically stitch molecules together. Okay? Okay, so we're done with chapter 13. I'm going to jump into chapter 15. Chapter 15, which is benzene and aromaticity. So we're going to learn lots about benzene and reactions of benzene, all the structure of benzene, all those kind of things. That's going to be in PowerPoint starting now. Alright, so we're into chapter 15, benzene and aromaticity. There's some PowerPoint, and there's some couple reactions, and then chapter 16 kind of continues with the theme of reactions. So I'll learn some here, and then we jump into 16. Alright, the reactions will be sort of my normal camcorder, whiteboard type style thing, but we have some properties and things to talk about, and there's two PowerPoint lectures. Alright, so first we're going to talk about introduction, nomenclature, and basic properties of benzene and aromatic compounds. So benzene is sort of the parent compound, and you've seen benzene before. It's 6 carbons, alternating single and double bonds. There's 2 resonance structures, right? You're a little familiar. A couple of the main points: it's super stabilized by resonance, so there's a lot of stabilization energy that goes into benzene, and the reactivity of benzene is typically through reaction with electrophiles. So E plus is a generic electrophile, and it gets attached, and there's a mechanism we'll go through all that later. An example is Br2. You also need FeBr3. Basically, it's not just an electrophile. It's called a super electrophile. It's got to be like extra electrophilic, and we'll explain why. But you can sort of understand why. This is super stable. If it's stable, it doesn't want to react. So how do you force something to react if it's really happy and stable? You need to kind of nudge it with a little bit of a more, like in this case, super electrophilic reagent. Pre-existing groups have substituent effects, and that's going to be the focus of the next chapter, chapter 16. So an example, if I have a benzene with either an electron donating group, EDG, or an electron withdrawing group, EWG, and I react these with electrophiles, so various E+ reagents. If it's an electron donating group, you'll see that the electrophile gets incorporated at the para position or ortho position. And then we say the EDG, the electron donating group, is an ortho-para director because it's directing things to the ortho and para position, right? This is the ortho, is the para. And alternatively, if you have an electron withdrawing group, EWG, and you react with an electrophile, then you get direction to the meta position, and that we call it a meta director. Meta director, okay? All right, so nomenclature. Aromatic, first of all, the word aromatic, it's sort of a historical word. I haven't gotten the full history of it, but you usually might think, oh, aromatic, maybe smells good or something. Well, a lot of these don't smell good. They don't smell. The benzene doesn't have the most exciting smell. It's kind of a nasty chemical smell. Indeed, it's carcinogenic, so you don't really. We usually don't like to smell benzene. Whenever you're pumping gasoline, if you drive a car, you are inhaling a little bit of benzene because it's in the mixture. It's almost like 20%, 10 to 20% of benzene. I'm sorry, 10 to 20% of gasoline is benzene. So, that's a little bit of the gasoline smell that you might know. And anyway, yeah, some aromatic compounds smell really nice. And yeah, but not everything. So some of the monosubstituted aromatic compounds, well, might be, what do you think this might be called? It's something benzene. Something benzene. There's a chlorine on it. It's chlorobenzene, right? Chlorobenzene. That looks like a, well, I don't know if you know what that is. That's a NO2. It's a nitro group. So it's a nitro group on a benzene. What do you think it might be called? Nitrobenzene. 2 carbons. Not a methyl group, but a ethyl group, and that's ethylbenzene. Okay, disubstituted. So we talked about ortho, meta, and para. Let's see examples of them. Okay, so this is an ortho, right? So the two things are next door to each other. You might give it a name like something bromochlorobenzene. Something bromochlorobenzene. If it's ortho, it might be ortho bromochlorobenzene. Okay. This looks like it's meta, so it's there's a difference, of an extra carbon between them. Chloromethylbenzene, maybe, and we're using the alphabetization like bromo and chloro. This is chloromethyl, so it's meta chloromethylbenzene. Meta. And we build the name from the right to left sometimes. Meta chloromethylbenzene. Okay, now we have what appears to be an ethyl group on one side and a propyl group on the other. And is this ortho, meta, or para? It looks like it's para. So it's para ethyl propyl benzene. Para ethyl propyl benzene. You can also give them numbers like 1 bromo 2 chlorobenzene, 1 bromo 2 chlorobenzene, 1 chloro 3 methylbenzene, 1 ethyl 4 propylbenzene. And sometimes also the ortho, meta, and para is abbreviated. What do you might think it might be abbreviated as? O, M, or P. Okay. Okay, so trisubstituted. So for trisubstituted, we number from the lowest alphabetical substituent, and so we start from the lowest alphabetical substituent, and then we number such that we get the lowest set of substituent locations, if that makes sense. We'll see it. All right. So, for example, here it's bromo is going to be 1, and it's going to be 1 bromo 3,4-dimethyl. 1 bromo 2,3,4-dimethyl. Okay. 1 bromo 3,4-dimethylbenzene. 1 bromo 3,4-dimethylbenzene. It's not 1 bromo 4,5-dimethylbenzene, which is 1, 2, 3, 4, 5, right? It's not that. Okay, so this is trinitrobenzene. It's 1, 2, 3 trinitrobenzene. But you could also say it's like a 1, 2, 3, 4, 5, 1, 5, 6 trinitrobenzene, right? 1, 5, 6. But that would be a little silly. And we like to give it the lowest set of substituent numbers. So it's 1, 2, 3. Common names. And so we won't, I don't have you memorize common names. There's a gazillion of these. There's so many common names, and you just see them and get used to them, but it's not something you'd usually get tested on. Okay, so one of them, of course, is methylbenzene, which is also called toluene. What if you have two methyls? It's called xylene, and this is orthodimethylbenzene, which is xylene. So xylene means dimethylbenzene. Of course, there's also like a metaxylene and a paraxylene. 3 methyls is called, well, in this case it's 1,3,5 trimethylbenzene. Trimethylbenzenes are called mesitylene. Mesitylene. I think when you did the NMR chapter, we used this as one of the examples, which had a very overly simple NMR, right? Because there's a lot of symmetry. Anyway, it's mesitylene, 1,3,5 trimethylbenzene. If you have an alkene on a benzene, of course an alkene is a vinyl group, and so it'd be called vinyl benzene. And that's also called styrene. And you know, I'm pretty sure you've heard of polystyrene before, like styrofoam. And that's essentially this stuff that's polymerized, so turned into a polymer, a plastic. So methoxybenzene is also called anisole. Hydroxybenzene is called phenol. And aminobenzene is called aniline. Not alanine, which you can Google that. Alanine, of course, is the amino acid. A-L-A-N-I-N-E, alanine. So aniline and alanine are sometimes confused by new chemists. There's definitely more in the book, and you know, again, a gazillion of these, and you just kind of learn them from time to time. It's not something that's you usually get quizzed on or tested on these common names. A couple more kind of, you know, just interesting compounds in society. Vanillin is a aromatic aldehyde, so it's a benzene with an aldehyde, and it's got a methoxy group and a hydroxy group. What do you think it smells like? Like strawberries? I'm just kidding. This is like the intense vanilla smell that you've smelled or tasted like at a coffee shop. It's most of the kind of vanilla powder you see is actually synthetic vanilla, and it's you know, safe and it tastes good. Our bodies really like the smell of it, you know. Acetyl salicylic acid is also acetyl salicylic acid is what aspirin is. So the pharmaceutical aspirin, it's a benzene with a carboxylic acid and an acetate group down here. Tylenol is a simple benzene containing compound with a hydroxy group and a nitrogen and a acetamide. It's an acetate group attached to nitrogen. A lot of explosives are actually based on benzene. TNT, 1,3,5-trinitrotoluene. Of course, you know toluene, right? 1,3,5-trinitro are the nitro groups. Kind of anything with a bunch of nitro groups on the molecules, typically explosive, and yeah, it's a shock-sensitive explosive. This stuff's used in like dynamite and things like that. This is kind of fascinating to me that, you know, this is a pretty simple benzene-containing molecule, diisopropyl. Of course, we see the diisopropyl, right? Diisopropyl phenol, 2,6-diisopropyl phenol. It's called propofol. Propofol, and this is a super anesthetic that's used in surgery. It also has a lot of abuse potential. This is actually what Michael Jackson overdosed on. under his doctor's care, I believe. And the problem with it as a drug, it's such an incredibly simple structure if you compare this to morphine or things like that. But it's got a very low therapeutic index. I'm not really going to go into that much. It's just, this is a measure of kind of like how dangerous a drug is, right? So it's the LD50 divided by the ED50. That's lethal dose that would kill half of a population divided by the effective dose that would kill half of a population. That would be effective for half of a population. And you want something with a high therapeutic index, where like the dose that would potentially kill you would be a very, very big dose, and the effective dose would be a very small dose, right? A good drug is that way. In this case, it's a low therapeutic index, so the lethal dose and the effective dose are very similar, and that's what makes it so dangerous. Okay, so a little bit about the structure and property of aromatic compounds. Properties. Thinking about the beginning of organic 1, resonance forms contribute equally to the structure. So when I show this one and I show this one, that doesn't mean it's like going back and forth. It's not like an equilibrium, right? They're both present in equal amounts, I guess. And for that reason, sometimes we abbreviate a benzene with a little circle. Those are the pi electrons that are kind of in the middle of the molecule. The bonding, so it's kind of, because the bonds are kind of like a hybrid between the left and the right resonance form. Like the bond length is kind of in the middle of a single bond and a double bond, if that makes sense. And of course, the hybridization of all the carbons is sp2, and the bond angle is 120 degrees, and then the bond length, like to the CH, is kind of like a normal bond length, and it kind of assumes sort of a hybrid between a single bond and a double bond on the carbons, right? So let's pretend we have a theoretical model of cyclohexatriene. Like we could actually have this molecule exist and study it. Like we're able to purchase a bottle of cyclohexatriene. Cyclohexatriene would mean a cyclohexane with 3 alkenes, right? Looks like what we're calling benzene, but this is something we can study theoretically, like in a computer, right? And if we had this molecule, you'd say, well, the double bonds are 1.3 angstroms, kind of short because they're double bonds, and the single bonds are a little longer because, well, they're single bonds, and 1.47. But in reality, as you can see, for benzene, like the real molecule benzene, it's kind of in the middle of those two extremes, right? Okay, so and that's due to the resonance contribution of 2 resonance forms, right? Okay, so anyway, we'll talk about cyclohexatriene as sort of a theoretical molecule. It can't exist because, of course, it would resonate into what we call benzene. The electronic structure of benzene consists of 6 sp2 carbon atoms, right? That. Each p orbital overlaps with the orbitals of the neighbors, so you have kind of a cloud effect. It's really easy to see here that there's basically like a cloud above and a cloud below. Like that has basically 6 electrons, pi electrons, right? This also shows this. All the carbons are sp2, and the pi electrons are, well, they're the benzene pi bonds. They're kind of on the top and the bottom. And this is like the electronic structure that just shows that the electrons equally distributed around the benzene. Okay. Okay, so in talking about, when we talk about, it's stabilized by resonance, right? Benzene is stabilized by resonance. can we estimate the extent of resonance stabilization? And there's some calculations in the book about this, but we can just show this very simply. Okay, imagine you have cyclohexene, right? It's a single double bond. It's alkene, right? And we hydrogenate it, and a certain amount of energy is released, and you can measure it. And of course, when you hydrogenate cyclohexene, you get cyclohexane, right? And the energy is negative 28.6 kilocalories per mole. What's the name of that? It's heat of something. Heat of something. The heat of hydrogenation is the heat of hydrogenation. Okay. Now, if you have a second double bond, like up top here, a second double bond. If you have two double bonds, you'd think it would be roughly twice, right? So like we just take this number and multiply by 2. But there's actually a little bit of energy stabilization in this molecule. That's why it's not exactly, negative 58 or whatever, 57. Because this actually has some stabilization itself, because these two are in resonance themselves. There's some resonance conjugation, some energy, some stabilization of this molecule, right? Okay, so let's just go a step further and say, well, if we had this theoretical molecule, 135 cyclohexatriene, and we kind of estimated the heat of hydrogenation of it, we calculate it, it's almost 3 times this number. It's almost 3 times this number. Assuming you had it, and you'd kind of assume that if you had this and there was no energy, no stabilization of it at all by the alkenes, because it's a theoretical molecule, that you have this kind of big number for heat of hydrogenation. So what would you predict would be the case for benzene, right? Because benzene is more stable. We're expecting it to be more stable. So are we going to get a larger number or a smaller number than negative 78.9? Well, if you think about it, it's going to be kind of a stable molecule, so you're not going to get as much heat out. And in reality, yeah, it's actually a little bit more stable than cyclohexadiene even, right? It's negative 49.3, so it's actually a smaller number than negative 54.9. And so then we can kind of define the resonance energy, which is like the stabilizing force of benzene, to be negative 29.6. It's basically this number minus this number. I think that adds up. Yeah, and so the resonance energy of benzene is negative 29.6. Okay, and so yeah, it's a stable molecule, and the stability comes from all the resonance. That makes sense, right? So benzene produces negative 29.6 less energy than a hypothetical cyclohexatriene molecule because it's stabilized by resonance. Totally makes sense. Okay, so we're going to talk a little bit about the molecular orbital theory description of benzene. This is something we don't go into too much depth, and you'll see this again in like physical chemistry. It's a pretty complicated idea, and we don't want to get dragged into this too much. But you learn it in baby steps, and you'll learn a little bit more later. And it's kind of a theoretical concept. Okay, so we'll be brief. It won't be on the test or quizzes or anything. Recall the molecular orbital theory for sigma bond in H2. This is a good place to start, right? Think about the sigma bond in H2. It's just a simple molecule, H2, right? It's 2 atomic orbitals, AOs, and that makes 2 molecular orbitals, which are MOs, right? So you got your H, you got your other H, and these both have atomic orbitals, and the 2 atomic orbitals get transformed into 2 molecular orbitals. You have a sigma orbital and a sigma star orbital. Sigma is the bonding, sigma star is an anti-bonding. Okay, so as long as electrons don't enter the sigma star, this is actually a very stable molecule, right? And it's usually the case that the anti-bonding orbital is inconsistent with bonding, right? Now let's recall the molecular orbital theory for ethylene, which is a double bond. So that has a single bond and in the second bond, which is a double bond. And those are called a sigma bond is the first one, and the pi bond is the second one. So if we consider the pi electrons, there's two 2p atomic orbitals, which get translated into 2 pi molecular orbitals. Okay. Of course, we also have the sigma orbitals, but those are usually low energy and untouched. But basically, it's pretty straightforward. We got the 2 atomic orbitals. Those are the pi electrons. They overlap in a way to give you a pi orbital and a pi star orbital. Okay, and as long as electrons don't enter the pi star orbital, the bond is intact. But when electrons enter the antibonding orbital, that will break the bond. Okay, and this kind of shows it also. We have like 2 carbons that kind of would overlap, and then you have basically a pi orbital and a pi star orbital. The pi star orbital is unoccupied because if it is occupied, it breaks the bond, and there's a kind of a node which is like basically it's inconsistent with the concept of a bond. The bond kind of requires an overlap, and when the pi star gets occupied, it's not consistent with a bond, and the bond is broken. The sigma bond might still be around, but the pi bond's gone. Okay. Note the node between the bonding and the antibonding orbitals. Okay. The pi does not have a node, which is just a continuous cloud of electron density, and then the pi star sort of has a node, which cancels the bond. So benzene has 6 2p atomic orbitals, right? Because there's 6 atoms. There's 6 2p atomic orbitals, right? And that makes 6 pi molecular orbitals. 6 pi molecular orbitals, all right? So, but this gets a little complicated because how do you draw 6 pi molecular orbitals, right? So 3 of them are going to be bonding, and 3 of them are going to be antibonding, and it looks something like this. So you got 3 that are bonding, right? And there's 6 electrons, so they're all full, 2, 2, and 2, right? And then you have 3 that are antibonding, okay? That is a pretty nice way to see it. Of course, there's other ways you can graphically visualize this. This is another kind of way to show it. And what you notice is at the very lowest energy, there's no nodes at all. So and you know what, when we say plus and minus, it's not like charge or something like that. It's kind of like a phase of a wave function, which is it's a little hard to appreciate, and you'll learn more about this in PChem. But basically, this is the lowest energy one has the most consistent bonding, but there's also 2 other molecular orbitals, and they have some extent of nodes in them, but they're still consistent with bonding. The anti-bonding ones have more and more nodes, and they, when they get occupied, they would cause the breakage of the pi bonds in benzene. Okay, that's one way to visualize it. But again, you learn about this more a little bit in PChem or something. You'll definitely hear about this more in your career. We don't really talk too much about this in organic chemistry. Spectroscopic. Okay, so let's just talk a little bit about spectroscopy of aromatic compounds. You already know this, but it's a little bit of a review of some of the like NMR of aromatic compounds. Okay, this isn't totally new to you. So a molecule like dimethylamino anisole, which is a dimethylamine group and a methoxy group. Is this ortho, meta, or para? Well, it looks para to us, right? That's very para. And let's look at how many CHs if it's para disubstituted. It's 4, right? 1, 2, 3, 4. You should be able to calculate the degrees of unsaturation of this, right? And get the right number. Remember, oxygen you ignore, but nitrogen you subtract an H. So it kind of becomes C9H12. C9H12. So this 2 times 9 is 18. Add 2 is 20. 20 minus 12. 20 minus 12 is 8. Divided by 2 is 4. And that makes sense because there's a ring and 3 double bonds. It's just a benzene. There's no ketones or alkynes or any weird stuff, right? Okay, but and for the most part, this NMR is straightforward. You got a pair of doublets, 2H each, right? Is para disubstituted. And then you have a 3H group and a 6H group. What do you think is which? Do you think is which? Well, the 3H is probably the methoxy. The 6H is probably the methyl CH3s. Generally speaking, oxygen pulls things down a little bit further to the left. So usually, if you have an oxygen and nitrogens, the oxygen shifts things further, like 3.7, versus here it's like almost 3 for the dimethylamino. The C13 NMR is not that exciting, but you got a couple peaks. These are all aromatic, right? And you have the really small peaks. Remember, are the quaternaries, which have no CHs on them. So it's these two little peaks, and then you get these, which are the big CHs, aromatic CHs. They're mirrored. So these two are the same. Or these two are mirrored, and these two are mirrored, and that's why there's two big peaks. Then you got a small peak and a big peak, and I think the small peak would be the single CH3. The big peak is the two CH3s, right? That's just a little more, reiteration of how carbon NMR works. Methyl Salicylate, which is oil of wintergreen. It smells really cool, like a wintergreen chewing gum smell. It's a ester. It's a diester. There's methyl ester and this kind of acetate ester down on the bottom. UN. You should be able to calculate UN of this. 2 times 10 is 20. Ignore the oxygen, right? 20, and then add 2's 22 minus 10. 22 minus 10 is 12. Divided by 2 is 6. And of course that makes sense because there's 4 UN in the benzene, and you have the top ester and the bottom ester. Okay. Proton Nmr is really straightforward. It's ortho, right? And ortho is 2 doublets, 2 triplets in some kind of order in the aromatic region. So it's doublet, doublet, a triplet, and a triplet. And then you have the one CH3 and the other CH3. The assignment of these is easy because one is connected to the oxygen, right? And that's the downfield one, 3.9. The other one's next to a pi bond, next to the ester C double bond O, and that's the one that's about 2.3. So this matches our chart like perfectly. The aromatic, there's not much to really say here. The tiny peaks. Oh yeah, two downfield tiny peaks are the 2 C double bond O's, the 2 C double bond O's, right? The esters, 160, 170. These 2 small peaks are on the aromatic ring. We don't know which is which. It doesn't really matter, but those are these 2 on the aromatic ring. And then you have 4 CHs, big CHs, right? And then you have one downfield CH3, the other more upfield CH3. The downfield one would correspond to the downfield CH3 in the proton, which is the OCH3, right? These are the same. And then this one, small one, and this one are the same. So that's the CH3 on the ester. Okay, I think that's it. Cool. All right, so we'll jump into the second PowerPoint next time, and then we'll get into the reactions and stuff after that.